4.7. Identify the necessary conditions for total internal reflection with reference to the critical angle. So I've got a few things on my slide that I'd like you to copy down, such as my underlined part on how does total internal reflection occur, also how to calculate the critical angle, and then just a short summary at the end of both of those. I recommend you read the first dot point and the different cases described in that diagram. So let's go through it. Total internal reflection is used to create binoculars along with fiber optic cables for communication and medical purposes. It is important to note that although known as total internal reflection, it is in fact a special case of refraction. So how does this occur? So for total internal reflection to occur, a wave must be traveling from a denser medium into a less dense medium, so the wave bends away from the normal. The diagrams below on the right illustrate situations of refraction that can arise when waves travel from a denser medium to a less dense medium. So in case 1, you could observe a ray of light being refracted further from the formal in the less dense medium. One could observe in ray 2 that a ray exactly along the boundary of the media. The angle I, which causes the ray to refract at 90 degrees, is called the critical angle for the medium that the ray is leaving. So in case 3, you can observe the ray being reflected back. However, it is actually the ray bending back past the boundary at more than 90 degrees. So the critical angle is the angle of incidence required for a material to cause an angle of reflection of 90 degrees. To calculate the critical angle, it is simply a matter of using Snell's law. Okay, so total internal reflection is when the reflection of the light when the incident ray strikes at a boundary at a greater angle than the critical angle. The angle of incidence corresponding to the angle of reflection is 90 degrees.